Introduction. This study compares three plant configurations: Power B, high steam, and high steam mixture as gasification agent using advanced exergy and exergoeconomic analysis methodology that allow not only for the evaluation of thermodynamic efficiency but also for the quantification of the economic impact of laws and investment in health components. System simulation and modeling. The first step was the simulation entry biomass gasification and oxy-fuel combustion system using Aspen Plus software. This program allows the different components of the system and their interaction the to be modeled, such as pyrolysis reactor, the gasification in the gas turbine. Operating conditions. The operating conditions are found in Table 1. Compressed pumps, turbines, condensers, heat exchanger, reactor. Physical and chemical properties. Civil dose, ultimatic, and proximity analysis for different biomass source. Describe the physical properties of fuel, which are crucial for the design and efficient operation of combustion equipment from initial to final analysis. Table 3. Standard chemical exergy of main constituent in ring. Standard chemical exergy reference energy real B chemical condition standard. The simulation validation in table 4, we can observe that the data present in the validation show values close the real values, which indicates that the simulation is in line with the actual operation. Assumption gasifier here of the 0.2, S relation B 0.8, and preheated relation power cycle and difference of 10 degrees Celsius, and compressed efficiency of 19, is gas turbine efficient 93.5 easily, and combustion churn and reactor temperature 811 Kelvin, exit temperature of 1773 Kelvin. Associated cost of the system uses steam as gasification agent. Total exergy destruction cost $15 hour. The system higher as the lower exergy destruction cost around $13 hour, and the mixture steam while cost close to $14 hour. In other associated cost of the system that steam has the high total cost exceeding $415 per hour, and the system that uses is lower total cost approximately $375 per hour, and the mixture of high and extreme fall between the two while about close the $425 per hour. Cost calculation methodology for the determination of the structure exergy. The exergy cost was determined based on exergy economic endogenous, exergoeconomic exogenous, exergoeconomic absolute, and exergoeconomic unabsolute.
Now, let's dive into the core methodology that advanced exercise basis in analysis framework. This is not a simple exercise balance. The researchers construct the total exergy destruction in any component into the more insignificant categories. First, they split it basis on origin. Endogenous deconstruction is the inefficient inherent of the component itself. Exogenous deconstruction is the part caused by the inefficiency of the other components interacting with it. Then they split it basis on potential for improvement. Unavailable deconstruction is the theoretical minimum limited by the current technology and economy. Available deconstructions is the portion we should actually target for improvement. Finally, they assign a monetary cost to this deconstruction. The key concept here is the cost of destroying exergy is calculated using the unit of the fuel entering that specific component. The powerful decomposition is the engine behind all the tight results we'll see next. This slide delves deeper into exergonomic analysis. Introducing the formula of the cost investment is advanced breakdown. We calculated the capital investment cost CK. The investment cost is split advanced categories. Endogenous investment is the cost lacked the component own inefficiencies. Exogenous investment, the extra cost for the other components inefficiency. Unavailable investment is the minimum investment required. Available investment is the cost that could be saved by optimizing. The available cost is the kind of coin. It tells an engineering world focus in the greatest economic return. Now, let's examine the key results. This slide compares three gasification systems: air, steam, and air steam. Table 6 shows the conventional exergy analysis. The steam-based system has the highest efficiency at nearly 50%. Our results are validated against another published works. Figure 1 visualizes the trade between product exergy and exergy destruction. The steam system generates the most product. However, the advanced analysis in Table 7 reveals a deeper story. Look at the available exergy destruction column. This is the potential for improvement. There is a negative value and exergy energy destruction. This means this interaction between components helps to reduce over irreversibility. Figure 2 compares the available and inevitable destruction. The steam system has a significant room for improvement. Let's now look at the economic results. Table 8 shows analysis associated cost. They can figure it to the net present value and NPV. The NPV is negative for all three systems. This means no one's plans will profitability investment. Table 9 breaks down to the early exergonomic cost. The steam system has the highest cost for the product. It is also the highest investment and destruction cost. The air system lowers the total cost, and the negative MVP tells that optimization in economic necessity. This slide provides the most profound insight. Table 10 split the cost exergy destruction. The K column is available cost. This is the monetary value and inefficiency we can reduce. The air system has the highest potential for cost saving. The steam system has unavailable cost. Table 11 breaks down the investment cost. The steam system has a massive available investment cost. There is a huge potential to reduce this high initial cost. The air and air steam system have a lower total investment cost. In summary, the steam system high cost can be optimized, and the air system has the highest potential for optimational saving. This analysis shows us exactly where to focus. Table 12 lists each major component, shows available cost of exergy destruction and the available investment cost. The critical math visually derives this component. The most critical components are the top right corner. The gas turbine GT has enormous available investment cost. This is the target to reduce capital expense. The pre-cooler PC has a very high available exergy destruction cost. This is the target for improvement efficiency. The chart is a roadmap for engineers. Let's analyze the steam system components. Table 13 provides the details of the cost. The critical map gives the visual priority list. The gas turbine GT has astronomically high available investment cost. This is a biggest target for reducing the capital cost. The pre-cooler PC has a very high available exergy destruction cost. This is the major opportunity for improved efficiency. The heat recovery steam generator HRSG, the economic viability depends on the trajectory's cost. The roadmap here is even more defined. Finally, let's examine the combined air and steam system. Table 14 gives us the cost breakdown. The critical map visualizes the priorities. The gas turbine GT has a very high available investment cost. This is still the number one priority. The pre-cooler PC is the key target efficient against. There is a notable increase in the cost of other components, such as the high recovery steam generator as the compressors. Optimizing this component is crucial. The gas turbine is the newest in the financial change. In conclusion, this analysis provides a clear roadmap. There is not a single best system. The steam system is the most energy efficient but the most expensive. The air steam offers best short-term economic viability. The most powerful insignificant is universal. The components with the highest priority are always the same. Number 1, gas turbine GT due to its massive available investment cost. Number 2, pre-cooler PC due to significant available exergy destruction. Focus to enforce first these components. Here are finally a conditional recommendations. We propose a two-phase approach. Phase 1, short-term actions high impact. Focus the pre-cooler and the high recovery steam generator. Begin a redesign for the plant for the gas turbine. Phase 2, medium-term actions. Modernize the K compressors. The choice of the system depends on your corporate goal. Choose the system of maximum efficiency. Choose the air system for the best economic balance. The air steam system is for the thick budgets. This concludes our presentations. Thank you very much.